Yes, so today we have Paul Kenrick from Music Tribe, who many of you will know because he, of course, used to work and teach and research and whatever here. Now he's gone off to the dark side, enticed by
fame, glory.
Yeah. More machine learning you can shake a stick at. Yeah, so it's quite nice. Worked out quite nicely because last week we had this talk on using machine learning to accelerate computational methods, and now we're looking at machine learning signal recognition, I suppose, essentially. Well, we'll find out, won't we?
Yeah.
So, yes, thank you very much. Just going to get rid of that.
That thing there, hold on. Sat on top of your slides. Get rid of that somewhere, and then put it out the corner. That's problem solved.
Right, thank you very much, Paul.
Right, yeah, so yeah, thanks for having me. It's nice to be back. It's been some time, so yeah, I was quite keen to come and do this in person just so I can say hello to people as well. So, hello. Hi. But yeah, so I'm from, I work at Music Tribe, which is literally just down the road, not too far away. This was going to be a dual presentation with myself and Carlo, who is an old MSc student from here as well. Unfortunately, Carlo is unable to make it. He's not very well today. So I'm going to attempt to talk about what he was going to talk about. So that'll go extremely well, I'm sure. But yeah, so first I want to give a bit of an introduction to the company, what we do, then a bit of an overview of the AI team, who I'm part of. I'm going to introduce a few projects that I'm working on as part of so I'm part of the machine learning team. And then I'm going to try and talk about some of what Carlo does, and he's part of the perception team. So Music Tribe is basically a holding company, and it's kind of owns all of these brands, of which I'm sure probably some of you kind of know most of these. So it's a company in pro audio, so all of the stuff we do is kind of related to pro audio. For instance, Midas at the top, we make mixing desks, like TC Electronic. If anybody plays guitar, you might own a guitar pedal made by TC Electronic. They make very cool stuff. And Tannoy is a very famous name within PA. In fact, the name is synonymous with public address systems.
Sorry, I can interrupt you for 1 second.
Yep.
I don't think this camera share is working.
It's on.
Oh, you're down there, aren't you? Yeah, no, sorry, apologies. Keep going.
That's all right. So that's kind of, I won't go into any more detail, but we have all of these different brands, and Music Tribe is the holding company that sort of that contains them all. So we have a mission statement, which I'm sort of bound to talk about, but it makes sense in the context of this presentation. So we try and make music production cheaper, simpler, more creative. I mean, so all of this is about thinking about things from the perspective of the user, basically. Just give me 1 second. Obviously, value for money is important. You know, we want people to buy our products, and it's got to be, it's got to be affordable, simpler, and more creative. A lot of the work that we do goes into these last two things. So how can we make the user interface easy to understand, easy to use? You don't actually have to think about it. And it frees you up more to be more creative. And sort of facilitating creativity is what really the main goal of the AI team is. So that's kind of what we're talking about. Now, we've kind of stolen the AI team. So I'm from the AI team, but we call it, rather than artificial intelligence, we've invented a new buzzword, because everybody needs a new buzzword, don't they? And we call it audio intelligence. So when we talk about AI, we're actually sort of referring to audio intelligence, and we think we're really clever about that, don't we? But basically, thank you. Audio intelligence is a collection of technologies aimed at creating products that make sense of sound from a human perspective, and then empowers the user to be more creative. And this is what we're always thinking about when we're trying to kind of when we're working, when we're trying to make this stuff for our products. So, for instance, a lot of sort of professional audio technology is pretty complicated. So I don't know how many people in here have done some sort of audio mixing use DAWs. I mean, I'm probably asking the wrong crowd here. You know, there are going to be a lot of people who know a lot of stuff about mixing, mastering, and all that stuff. But we're interested in you guys, but we're also interested in the novice. You know, the idea is new users who haven't used this stuff before, it can be pretty daunting and complex, especially sort of modern digital mixing desks. If you ever used one of them, going through all of the different sort of channels, it's really daunting. So can we find a way to understand the audio and give a helping hand to novice users? But we don't want to do this at the expense of experts, you know, because a lot of the sort of initial kind of rhetoric from kind of experts was we don't need AI. Why do you want to give us AI? We know what we're doing, and I think that's fair enough, really. So it's about trying to find a way to present the information to the user in a way that's helpful. You trust the product, but it doesn't sort of you know, it doesn't annoy you. You know, that's I think that's a nice way to kind of summarize it. So we make a lot of different products using Tribe, but when I joined the team a little over 2 years ago, the main focus that I've been working on is this one here. So this is the Midas Heritage D96 mixing console, and it's a console that's used for live sound reinforcement for kind of large touring shows. It's only been released fairly recently. I think it's about when the lockdown happened, so not ideal. But yeah, so this is very cool. And what we've been contributing is a feature called the Channel AI. And this is a feature that will analyze the audio signal and provide some information to the user that is helpful, that is going to, you know, help the novice and speed up the workflow of the expert, so kind of thing. And I've got a short video that I'll just play so you can kind of see it in action and just give you a bit of context about what it does. So we'll see. There is sound. It doesn't really matter if you can't hear it. Hopefully you can.
I don't think I share the sound with the team.
But it's not so important at this point. Okay. The sound is just not important. But this is the desk, and if you see in the top right hand corner here, there's this little button called AI, and we're about to see a hand come and press it. There we go. And now what it's doing is it's capturing a buffer of audio from a particular channel, and it's profiling it. It's trying to work out what is the signal, in this case it's bass, and it's trying to work out, make some suggestions about audio effects and presets for those audio effects that are going to be helpful for that particular signal. So it's, we call these adaptive presets. So not only do they depend on, it's recognize what the signal is, it's also analyze the content, frequency, response, etc., and make some intelligent recommendations for the EQ presets that will be useful for this sound, for this application. That's the kind of idea. So in terms of how the audio intelligence team, AI team, kind of function, we're split into three. So, and these are kind of the three pillars that we think are important for getting audio intelligence into products. We've got machine learning. So I'm part of the machine learning team, and we're responsible for training models, evaluating models, and then releasing models, which will then go into our products. We have the perception team, and they're responsible for figuring out how can they use the information that we provide, from, what is that instrument, and some other things that we'll talk about in a bit, and some perceptual acoustic models to create these adaptive presets. So that's what Carlo would have been talking about here. He's part of the perception team. So the kind of models that we are working on, the obvious one is instrument recognition. What is that instrument that's playing in that channel? Voice activity detection is another thing that can benefit from machine learning. But we also look at music transcription as well, so audio to MIDI, and some generative models, which is kind of interesting. I don't really have time to get into that today. So then we have the platforms teams as well. The platform team basically takes the models that we've created, the ML models and the perceptual models, and they build a library that kind of operates, that uses these models, a library and a microservice, so that other people in the company can just take our stuff and drop it into their product. That's the idea anyway. So we're creating a kind of resource that can be shared across all of the brands. So as easy as possible, we want some cool AI in our product to figure some stuff out, we can just take our stuff and drop it into a product, providing it has the power to kind of analyze it. Of course, the HD96 does, it's quite a powerful thing. So, I wasn't sure who my audience was going to be, so my question here was going to be, I'm going to ask it anyway, is can somebody define machine learning for me? Go. Anybody know what machine learning is?
Statistics.
Statistics.
Experiential learning of a mapping from input to output from hypothesis.
I think that's pretty much the pompous description I wrote as well. So yeah, we've matched up. So basically, it's a way of getting computers to act without being explicitly programmed. So you've got some complex model. You can't write something that's going to go, right, I know that this particular frequency response combined with this harmonic series is going to tell me that this is a guitar versus this is vocals. It would be, you'd go crazy. So what we do is we have a lot of data and we try and learn the underlying mappings from it. So you can discriminate between the guitar and the voice, etc. So that's kind of, in a nutshell, machine learning. There's a whole bunch of different types of machine learning. I'm not going to talk about all of them. I'm mostly just going to talk about supervised machine learning. So this is, so could I just ask in terms of, so what courses have you, I know you've got some postgrads and PhD students. Do we have anybody from the MSc here? Yeah, and anybody from the undergrad courses at all? Hello, okay, so we've got...
Two MSc here actually, so we've got the MSc Acoustics, Audio Acoustics. You do machine learning stuff for Francis, and then you guys are more like production, so I'm not quite sure what you do.
It's called magic, John. I mean, that's audio production. Yeah, yeah. Okay, well, it's good to know. So you guys, have you started doing the machine learning module yet?
I have, yeah, I've already been through.
You've been through it. Okay, cool. So yeah, you know, there's different types of machine learning. I'm mostly going to be talking about supervised. The idea in this case is we've got a section of audio. It contains a musical instrument. What is that instrument? We've got so we have some data. For our training database, we have labels, so we know that there's vocals in this particular section. So as an ML engineer, I've been mostly spending my time dealing with data, kind of the actual training of models and that kind of bit that most people think about is such a small part. It's mostly about how you set up the database, how you need a large quantity of well-labeled data. You need metadata on that data as well, so you can slice through it and kind of, if you end up with problems with your classifier, you need to understand why you've got those problems, and having different ways to slice through your database is important. So we need, well-structured, lots of information about the data and accurate labels. What we have is we've got separate databases. We've got a training database, and this is effectively, in this case, they're multi-tracks. So we've got multi-tracks from live situations, multi-tracks from studio recordings, and we also have kind of isolated instrument recordings, like sample libraries and things like this. So we have a training database. We have two other databases as well. We have what's called a development database, the idea being that we can assess the performance of a model using the development database and make changes and basically tune it based on this development database. And then we have a separate, all of these are separate, and we have a test database that tells us how well is this going to work in reality. And the whole idea for these development and test databases is these need to represent the data that you want it to do well on in the future. So you always got to have that in mind. So we want it to do well for live multi-tracks, particularly for the HD96 system, that was our target, but we're moving into other areas, so we're looking at studio multi-tracks and other situations as well. So I'm going to talk about two things that the machine learning team has been working on recently. The first is onset detection, so kind of detecting where notes occur within a recording, and the second one is instrument recognition, so what is that musical instrument in that recording. So firstly, onset detection. So this is a method for detecting the moment an audio event starts. So it could be, the point where the snare drum hits the snare drum, or it could be, the point when you first utter a word. This is the idea. Why do we care about this in particular? Well, this information is extremely useful for things like if we want to do beat tracking. If we kind of process the audio, extract the onsets. We've got a much easier way of kind of doing beat tracking. Groove extraction, if anybody's used Ableton Live, it's got a groove extraction feature. You can extract a groove from one signal and apply it to a different one. It's super cool. It also accelerates the editing process. So if anybody's done audio production and recorded drums with maybe not the top of the line drummer, editing drums is a nightmare. You know, if you've got a way of kind of slicing up the audio automatically, and a lot of stuff does this nowadays, then you can kind of fix it in the edit, as they say. And you can also use it as a foundation for kind of other downstream tasks. So once you've segmented the audio into onsets, you can define it as an event, a single event, and then you can classify that event. So you can kind of split up the audio and learn more about it, which is how we use it. You can also use it for F0 estimation pitch, estimating the pitch of signals, so you can do transcription as well. The onset detection process this has been around for years. So the sort of one way of doing it we call the DSP method. This is how the cool people do it. What you do is you've got your original audio signal, apply some sort of pre-processing, whatever it might be, but then you're trying to reduce it to a simpler representation, which we call the activation function. So this is basically some representation where the onsets are clearly visible, much more clearly visible than in the audio itself, is the idea. So it could be the energy envelope, it could be some sort of region in the spectrum. For example, high frequencies is a good indicator of percussive sounds, or it could be changes in the spectrogram. For instance, spectral flux is another good one. So once you've got your activation function, it's just a matter of a classic sort of computer science problem, which is peak picking, which I'm sure if you've used MATLAB, which I'm sure you all have, has the peak picking function built in, but it's about applying peaks to this function. And again, there's loads of stuff that you can do to improve it here, which I won't go into. So this is how the cool people do it. The cooler people do it using machine learning, which I would say, because that's how we do it. But the way that we do this is we have a corpus of data which is being annotated by people who are domain experts. So I'm basically talking about sound engineers, or more likely sound engineering students who want to earn a bit of money to do some annotation. So what we then do is, once we've got these annotations, we extract some features. So this is what we generally do in machine learning. In this case, spectral representation, short-term Fourier transform is a good option. And then what we do is we train a binary classifier on a very short section of audio. So think of a really short section of audio, and the binary classifier is there an onset, or is there not an onset in the middle of this section of audio? Yeah. Then you scan over the audio, and every time there's an onset, something will pick up like this, and this creates our activation function. So this is how you train it, and this is how you create this sort of state-of-the-art onset detection methods. We've got a system that works really rather well. You can then go even further for the peak picking. Simple way of doing it is just a threshold in the activation function, or you could post-process the activation function. For instance, you could differentiate it. Often that will kind of accentuate these beginning peaks. Or there's other machine learning models that you can apply that will have kind of prior knowledge. For instance, it could learn about where's the expected beats going to be, so you can kind of get greater accuracy. So we've tried all sorts of things. It's not really. We've actually found the threshold is pretty much is pretty good. So we didn't get much of an improvement with doing any more complicated stuff. So that's onset detection. It's now on to musical instrument recognition. And what I want to do, I'm introducing it with the classic problem, which is kazoo versus bagpipes, which is what you always think about when you think about instrument recognition. And I know you were all thinking it. Yeah. So I just want to talk about what people have done in the past. So in terms of what's done in academia, and if you look at the literature, this is how it's talked about. So you've got the starting point is monophonic instrument recognition. This is where you can guarantee there's only going to be one instrument there at a time, which of course kind of a bit of a prior here. So this started off doing this on isolated notes. Then you can go on to kind of longer recordings, solo recordings. But yeah, basically you're trying to predict a single label from a piece of audio. That's effectively what the machine learning problem is. Like for our problem, obviously, kazoo and bagpipes is maybe not a good choice. So we have a selection of maybe 16 instruments we think are kind of important for our customers, and it works quite well on those. So it all depends on what data you have, as to how and what data you want in terms of what instruments you can predict. Anyway, so this is monophonic instrument recording. The next stage would be polyphonic instrument recording, because of course, if you've got a recording, in particular, if you've got a microphone over a drum kit, you're going to capture a lot of different sounds, you know, from bass, guitar, or drums, etc., etc. So this is the next stage. So there could be many overlapping events. So what this is attempting to do is attempting to go, oh, there's a kick here, here's the start and the end, so that's the onset and the offset, here's the start and the end of this kick drum here, got a bunch of snares. So this is, as you can imagine, an extremely difficult task. So you can do it, you can train a machine learning algorithm to do this, but effectively it's transcription, especially for a drum kit. You're basically working out which drums are where. Effectively it's transcription. To train a classifier to do this, you're going to need a huge amount of extremely well annotated data. So you can think how long that's going to take to do. So when I was working here as a researcher, I used to do annotation of birdsong, which is exactly the same problem. It takes an extremely long time to create these annotations, very challenging to do. So there's a slightly easier task, and everybody likes a slightly easier task. The slightly easier task is, you could call it predominant instrument or instruments classification, or tagging is easier. So basically, given the same chunk of audio, you just say what's in it. So it's a lot simpler. So we call this weakly labeled data, and this is kind of strongly labeled data. It's much easier to get hold of this data than it is this, but this data is less useful, obviously. So there's a kind of trade-off. You can kind of see a trade-off. If you reduce the size of this window here, obviously you do more and more tagging, but it's getting closer and closer to this here. So these are the kind of, you've got monophonic and polyphonic, and within polyphonic, this is two kind of, I kind of view them on a continuum ways of doing this. But I just wanted to mention a similarity to environmental sound classification as well. So this is a, this is a very, very similar problem. So rather than telling what the musical instrument is, we've got acoustic scene classification, which is what is this soundscape? So is this a zoo? Is this a park, etc. And then acoustic event detection, which is within that soundscape. There's a dog here. There's somebody roller skating there, etc. Kind of go through it. So they're quite similar problems. And actually, you can think of monophonic instrument recognition, where you're trying to estimate a single label, as being pretty much the same as acoustic scene classification, where you're trying to predict the same label. And polyphonic instrument recognition, again, music event detection, it's very much the same as acoustic event detection. It's basically you're just transcribing what's happened within that period. And again, you can do tagging in both of these. Now, the reason why I mention this is that there's an awful lot of work that's done with environmental sound classification, and I would say more so than musical instrument recognition. So in particular, you'll know about the D-case challenges recently. They're very, very popular, and what's really useful for me is I can use those that technology, those ideas, and apply them to musical instrument recognition, which a similar event is called Mirex, which is a lot less popular. So you maybe have 1 or 2 entries in Mirex and hundreds of entries in the D-case challenges. So you can see what is the state of the art in there. So it's quite interesting to think about this, and you can use that technology. I want to kind of look at this from a different perspective again. So we've thought about instrument recognition in terms of what the literature talks about. We've thought about environmental sound classification and its similarities. And we need to think about it from our use case. So basically, we need to think about this from the perspective of the user being the sound engineer. So what does the sound engineer want? What do the signals look like is the kind of thing we need to think about. So most channels are going to contain a mixture of sound when you record a band or whatever. You get something called still. So this is sound that's picked up from a microphone other than the source it's intended. So, you know, for instance, if you've got a microphone under the snare drum here, it's going to pick up the snare drum, but it's also going to pick up the kick, the tom, etc., etc. But that's the character of that signal. It's not necessarily that we're trying to identify, you know, the instruments within the signal. We just want a label. It's actually quite a lot simpler. So we don't want to do polyphonic, you know, instrument kind of detection to apply a label. We just want to learn something about the sound. What's interesting is if you think about, in particular, the snare. So often what you'll do is you'll have a snare on the bottom and a snare on the top. Both of them capture the snare drum sound, and both of them capture a lot of spill from the other surrounding drums, but they have a very different character. So the bottom snare captures the resonance of the snare itself, and it has a lot of sympathetic resonance when the other drums are sounded as well, whereas the top one doesn't. So if a sound engineer listened to those two sounds and went, yep, that's the snare top, that's the snare bottom, very easy. And in fact, a machine learning algorithm can do that too. So I kind of think that actually this channel label prediction is not really musical instrument recognition monophonic. It's more like acoustic scene classification of lots of different versions of the soundscape, especially from a drum kit. So you kind of, in particular the overheads as well. So how do you know the difference between the overheads and the room microphone? You know, they've both got kind of similar distribution of levels, but they've got a different character in terms of the amount of reverberation, probably. So this is kind of how I think about it and how we think about it. We think about this as being this single channel prediction, but it's a bit more like acoustic scene classification than instrument recognition. Now there's another thing to think about. So we can apply a single label, we can predict a single label to a channel, but it is useful to know what other instruments are in that channel, because you can then go, okay, there's spill from the kick drum, there's spill from the hi-hat. So what we do is I then say, well, then if we can do polyphonic instrument recognition, this in our context is a bit like spill analysis. So if you know what the channel is, this is a snare drum channel, and there's a kick drum event identified, well, it's spill, you know. And this is what we do. So we do the monophonic or acoustic scene analysis, as I'm calling it here, to predict the label. And then once we know the channel label, we can do musical event detection and classification, and this will tell us what's spill, what isn't spill. So it's actually quite a simple idea. In practice, very difficult. As you may have mentioned, it's all about data. So the problem is, how do you get all of those kind of lovely annotations? So yeah, as I said, we collect 3 types of data: studio multitracks, live multitracks, and some isolated recordings like sample libraries. And what we have is an extensive data curation process where first we ingest this data. So again, this is what I've spent a lot of my time on recently, trying to automate this process because it's rather painful. You know, reject sounds that are corrupted, reject sounds that are distorted, perhaps. And then we need to label it. So if you can extract the label from the file name, so if somebody has called this kick 1, then that's useful information. It saves you a job further down the line. So yeah, we have systems that attempt to do automated labeling at a channel level. But ultimately, there's always going to be some level of annotation required. But channel annotation is not really that painful because you can just listen through a multitrack fairly quickly and go, if you're a domain expert, if you're a sound engineer, it's not too bad. You can go, yeah, that's clearly a hi-hat. I can hear the open hi-hat really loudly. It's not too painful. What is horrendously painful is event annotation. So we've done bits and pieces, but ultimately there's no way that we can annotate our entire training database with individual events. So most of my research the past year is kind of focused on how do I avoid doing event annotation, because it doesn't scale. You can't scale it. So we have various solutions for this. So we use TensorFlow for training all of our models, and then we use TensorFlow Lite for deployment. So TensorFlow Lite is a version of basically you can parse a TensorFlow model into something that's a lot smaller, more compact, and more efficient, which is not quite compatible with TensorFlow, really annoyingly. But this is how we then deploy the models on what we call edge platforms. So this would be the HD96 and a guitar effects pedal, if that was the platform. The way our system works is you analyze a 3-second chunk of audio, just a single channel. We tried to make it as simple as possible. We didn't want to get to the point where we were doing a multi-channel analysis, because that basically places a lot of computational load on the product. So we're just trying to make it simple and single channel analysis. And the task is, what is the channel label? So in terms of our database, I'm not going to go into detail, but basically the way we've set it up is we can make slices through our data based on the instrument, obviously, but then we have other sort of properties and metadata that we can slice. So for instance, if I only wanted snare drums from the top, or if I only wanted kick drums which were inside the kick drum, not out of it, or if I only wanted to create a instrument classifier that worked for death metal, you know, we could do that if we liked. You know, that may be a thing, I don't know, but we can make slices through the data. We then, once we've got this slice through the data, we then have a system of streaming raw audio into our, we have GPU enabled machine. Some stuff's done in the cloud, although some stuff's done locally, for then training the model to predict a particular instrument label. We also have kind of something interesting where we add some heuristics to the output, where there's different ways of doing this, but we add some heuristics to the output that can inform downstream when the classifier is unsure. This is really important. So when the classifier makes a prediction, oh, that's a kazoo, and actually it's bagpipes or whatever. But you can see, you know, just from the softmax outputs for a simple classifier, if it's unsure, and you can pass that information further down the line. Or what we have been doing is using Bayesian neural networks, where the uncertainty is inherently learned within the model, which is super cool, but super computational heavy. So often we kind of revert to the simpler model. So yeah, this is kind of where I think the sort of fun bit kicks in. So you know, doing all the data is kind of quite a lot of hard work. But yeah, the fun bit is once you kind of set up your database, you can then start asking interesting research questions and you know, look at different feature representations, which feature representations work best. So short-term Fourier transform, wavelet scattering transform, or some learned feature representation. So you can do some kind of interesting stuff here. Now you've set up your databases. What we've done is our feature extraction is embedded within the TensorFlow Lite graph. So within the TensorFlow Lite graph that we pass to our production team, everything's contained within there, so they can just use that. So it makes life a lot simpler for them, but makes life quite difficult for us, because there's a lot of stuff that isn't compatible between TensorFlow and TensorFlow Lite. For instance, fast Fourier transforms. Amazingly, they don't work in TensorFlow Lite yet. So we found ways around that. So the way that we kind of assess our models is we use something called optimizing and satisficing metrics. Satisficing is an interesting word. And the idea is it's very useful just to have a single metric where you can say this model is better than this model. You don't want to be looking across 12 different parameters, which of course you can do. If you've done much machine learning, I'm sure you'll have looked at confusion matrices, which is still useful. But if you want to say this one's better than this one, it's very useful just to have a single metric to compare. And that could be something like F1 score or Matthews correlation coefficient, or even accuracy, depends on what the application is. So you have kind of one metric which you kind of make choices and decisions based on your research question. But then we also have these satisficing metrics, and these are more like thresholds above which we can accept this model. So an important one for us is inference time. You know, this thing has to run on the edge, so it needs to be quite efficient. So we measure the inference time. If it goes above a threshold, then we say, well, it's great, but it's no use to us. And model size as well, because memory is an issue. So this is kind of generally how we do our experiments. So this is for the channel labeler. Then for the still analysis, so the channel labeler is acoustic scene classification. Still analysis, we're now going to try and do polyphonic instrument recognition on the same section of audio. And the way that we do this is we leverage our onset detector, and then we just downstream we classify each of the events. So it's fairly simple. So as I was saying, most of our work has been spent kind of trying to figure out how can we get these labels without having to label it all ourselves, or I mean, the other option is we pay somebody else to label it as well, but that's very expensive. So a lot of my research has been looking at ways to avoid doing annotation. I even had an MSc project student last year with Salford who was looking at this very. So he was looking at, can you use the concept of label noise? So if you've got an audio channel and it's a kick drum channel, and it's got kick, snare, kick, snare. The idea is that snare is an error. Basically, if you label everything as kick, okay, that's correct, incorrect, correct, incorrect. So can you then treat this problem as a label noise problem? And there's kind of solutions to this where you can iteratively change the labels based on some heuristics. I mean, he did a great project. Ultimately, it turns out no, you can't. But that's research, isn't it? It was a cool idea. And the reason is basically there's a particular character to spill. A snare drum in a kick channel is nothing like a snare drum in a snare channel. So this is the problem. So you can't do that. Now we have a solution for this. I can't really go into detail, so I'm going to have to leave there with the magic. I'm not sure I can kind of talk about that. So I'm going to have to say we have come up with a solution. It's not the best solution in the world by any stretch of the imagination, but there's loads of interesting research around this area that we're doing. So we've got something that works a bit, and that's how this thing works. But to go further, we want to try things like semi-supervised learning and stuff like that. So now on to the audio perception team. So I'm now going to morph into Carlo. So I'm now Carlo. So the audio perception team is responsible for research on both DSP, psychoacoustics, as well as the user interface design. So they're always trying to think from the perspective of the user. So they know that systems are going to be judged not only for audio quality, so how well is how well is it producing, how well are these audio presets changing my sound, but also from the user interface perspective. So if something's overly complicated, nobody's going to want to use it. So this is kind of critical. And what they've done is they've tried to adopt a user-centric approach. And I actually think that's the consistent theme that I'd like to kind of talk about through this presentation, is everything is from a user-centric perspective, even the machine learning. So we've kind of slightly rethought the problem of instrument recognition from the perspective of an audio engineer. So we're trying to think about it from a user perspective. And this is what the audio perception team is doing even more so. Now, the main challenge is actually trying to get AI accepted by professionals, because there's a lot of cases, and I've talked to a lot of engineers who've just gone, no, I don't want anything to do with this. I know what I'm doing. I know my job. And most of our work is trying to present this information to the user in a way that isn't going to do, it isn't a black box that does some magic stuff. It can interact with you, and you can find some interesting information. It can save you time, or you can choose to ignore it if you want. So that's kind of a lot of our work is done. So this is a snapshot of the channel AI on the HD96 console. Now, I want to kind of talk through how it works and how we kind of achieve that sort of it not being too in your face, this AI. So what you do is you press the profile button up here. This captures about 3 or 4 seconds of audio from the channel that you're on at the time, and it creates a profile. And this profile contains all of the information that's extracted from the ML models. So what is the instrument label? What's the spill? We also get, so this is indicated to the user here in terms of, is the spill present? What's the quality of the prediction? That's all kind of sent down there. And then rather than just labeling the channel for you, which you can imagine if you got it wrong, you'd be like, right, deleting that. So we kind of make a suggestion. So as soon as you can edit it here, and nothing happens until you press apply. So down here, what you have is a series of suggestive adaptive presets. So it's created, some EQ based on the signal, but also on what it thinks the instrument is. So if you had a guitar, you might want to boost a particular frequency to make it sound more aggressive. You wouldn't do the same thing with bass, but also it depends on what that guitar is. If it's kind of death metal, then you might not want to boost it too much. Whereas if it's country, you might want that twang. So that's what this adaptive preset is doing here. So yeah, I hope you can see it's trying to present that information to the user and let the user decide what it wants to do rather than just sort of enforcing it. And we're trying to I think you can call it, you're trying to establish trust. You're trying to get the user to kind of trust what it's doing. And you've got to accept that AI is never going to get it right. It's never going to get it right all of the time, I mean. So you've got to kind of present this information to the user in a way that they can accept. When it gets it wrong and deal with it. And that's a lot of what we're doing here. So this is the instrument analyzer, which is the system flow for the audio perception team. So basically, you've got some audio, you run it through the instrument classifier, we have some instrument labels and spill annotations, and then the instrument analyzer analyzes the audio, looks at the frequency response, looks at what instrument class it is, and then makes some suggestions for both gain levels, EQ, dynamics, and gate. So the gate in particular, which is what is kind of super cool, uses the still information that's provided by the instrument classifier. So what time am I on? Okay, no, that's okay. So what I've actually got now is I'm going to show our system in action. This is where audio might be required. I'm going to show our system in action. What we do for prototyping our stuff is we use Reaper. So I'm sure pretty much everybody knows what Reaper is. We use Reaper to prototype our system. So Reaper has a nice Python API. You can interface it with lots of other stuff. So we created a DAW assistant, which does all of this stuff. It takes our AI microservice and library and just drops it into this little app which sits on top of Reaper. And this lets us kind of show internally what we can do, because of course we've got the HD system, but also we want to kind of demonstrate it and quickly try out ideas, which I'm kind of going to show now, kind of what we've been doing.
So it won't actually do it.
Okay.
It's telling me to change some setting that's not working. So we might have to rely on the people hearing it through the microphone again, sorry.
Okay. I think, well, what I can do is maybe share the videos afterwards, which have got the sound on.
That'd be amazing.
Yeah, I'll have to ask Carlo, but...
It was picking up a bit of spill off the loudspeakers. Yes.
Spill.
Yeah.
I can hear it on my phone, it's good.
Okay, so what I'm going to show here is just a session. So, Reaper session. You see that? Yeah. And basically, we've gone from a kind of blank slate here. So we've got the audio multi-track for a particular song. We've got the audio channels. None of them are labelled. And what's going to happen is the DAW assistant's going to go through each channel and predict what the label is. Then it's going to predict and apply some presets based on the signal or whatever. Now, of course, we could have done this for real, but it would, in the time available and the fact that my colleague's not here, it just wasn't possible. So I'm afraid we have a video, but at least it gives you an idea of what goes on. So what's happening is it playing? Yeah. There might be some speech at some point, but yeah. So it's going through each of the channels and it's making a prediction of what the label is going to be, and you can see the instrument effects as being populated as it goes through. So you've got things like a gate, especially applied to a kick drum, compressor, EQ, as well as some multi-band dynamics being applied at the same time as well. So it's kind of, I hope you can kind of see what this might be useful for. If you are not a pro engineer, you just load up some multi-tracks and just go. It's super cool. But also, if you are, it might be something you want to use to save you a job having to label it. But that's another thing. So yeah, so you can see it's gone through all of the channels, and it seems to have got them all correct. I think this is a video. We might have selected the one that worked. It's pretty good. So yeah, so there you go. Now, what I want to do is, I'm going to do an A/B comparison. So we're going to play the audio. First, I can't remember if we play it without. I think it's first plays it without, and then with. Now it's important to say here, this is not auto mixing. Each channel has no idea what the other channel is doing. There are some gain settings that you can do to bring it up to similar volumes, but that's not really what we're trying to do here. This isn't auto mixing. This is basically saving an engineer a job, but you can kind of get the idea. What's that playing? Is that without? It's massively reduced the guitar, obviously, but the drums sound much better.
It's pleasing for me, but irritating for you that what the AI engineer does is the same as me, which is to turn the guitar down. Paul and I like, well, still do play about, don't we? And I'm always in trouble for turning.
It's a true story. It's a true story. I can't tell you how many times. John, can you turn on my guitar? I can't hear you over your bass. But yeah, that's the kind of that's the overview. What time are we at? Okay, so there is one more video. I think this one's a bit longer. We'll see how we go. I'll play it, but it just goes through the setup in a bit more detail, so it gives you a bit more of an idea of how it works. So the AI assistant, the DAW assistant rather, is this thing on the side here, and it holds all of the metadata and information that's being extracted by going through this process. It kind of works in the same way that HD works.
Hi, today I'm going to quickly demonstrate the DAW assistant and walk you through the main workflow of the application. So the DAW assistant is the application we use to create the A/B comparison which you heard earlier. So at the very top we have a drop-down menu that lists all of the audio channels that are currently open in the repair session in the DAW. So selecting a channel and clicking on the profile button will actually perform analysis on that track and return a snapshot. So a snapshot is essentially an object that encapsulates the following data that result from the analysis of the signal, of course. So that is some quality metrics regarding the quality of the buffer which we captured, the identified instrument class, as well as a set of adaptive presets for the following DSP units: trim, compression, EQ, and gate. It's important at this point to stress that these are actually adaptive and not static like the typical presets you will find in other DSP units or synthesizers, for instance. So they are adaptive and that they have been estimated based on the analysis of the buffer which we captured, as well as the instrument class. So let me quickly demonstrate that. I'm going to bring up the EQ of the bass, as well as that of the electric guitar. So they both have the corrected preset applied to them, but what we can see is that the frequency as well as the gain and bandwidth values are different between the two. And you can see that in here. So now let's have a quick listen at the adaptive presets for the guitar.
This is quite cool. This is corrective, so it's pulling out some frequencies.
We are listening to the corrective preset, as we can see here. That's the warm preset.
Warm.
And let's have a quick listen to the aggressive preset. You can see this sounds significantly different. And they are all estimated based on the analysis data.
Okay. So yeah, I think that'll do. It gives you an idea of how it works. I won't let Augustinus talk for me any longer. But yeah, so that's everything. So now I just wanted to see if there was any questions, or if you wanted to kind of talk about anything in particular. I think the main theme that I wanted to get across here is the sort of user-centric approach that we've taken. So it's not only it's kind of fairly obvious you need to take a user-centric approach from the perceptual team, because you're using your ears, but also from the ML perspective, we need to think about what ultimately is wanted, and it is that slight rotation of the instrument classification problem. So yeah, there we go. Any questions?